Welcome to website tutorials for our collision notes. If you have missed class today, please make sure that you pick up your collision worksheet in your hanging file folder, or you can get it off of my website on the worksheets page. So we've already talked about this picture. We've seen this picture before, and I'm just going to reiterate that we have two different types of classic elastic collision, and we're going to be working those two different types of questions on our homework for this particular lesson. So a collision in which objects collide and bounce apart with no loss of momentum. So we will start with two separate objects and then we will end with two separate objects. So like we mentioned in our previous lesson, bumper cars and pull are two examples of an elastic collision. In a bumper car example, both objects are moving towards one another, they collide and they bounce in opposite directions. In our pull example, there is one object that has been given an impulse that hits an object that's being still, and then that original moving object becomes still, while the other one, or the momentum, is passed on to the other object, or object number two. For our elastic collision, we have a equation where we take our momentum of our first object, and remember, momentum is the mass times the velocity, and we add it to the momentum of our second object from one side of the equation, which is equivalent to the momentum of the first object, but in this particular side, it's our final velocity that we are getting the momentum of, plus the final velocity and mass of object 2. So objects are moving at one point, they collide, and then there's movement at after that collision. And so we have to take that into account, and that's called the final velocity. So to make sure that you understand this mathematical equation conceptually, observe the two little, well, they're not little cars, but the big truck and the little car here. Notice that the data tables above them are changing. So we have their initial velocity, which changes after they collide. And you can see that the negative is going to represent the direction in which the car and the truck are going. So this animation is going to portray elastic collision between the little car, which is 1,000 kilograms, and the truck, that's a 3,000 kilograms. So here we see a before and an after collisions. We see their numbers and how their velocities, momentum change in our data table. So the little car starts out at 20 velocity, 20 meters per second, and it ends up with a negative 40 meters per second. Okay? You can notice that its momentum changes as well. Its momentum doubles for the car. For the truck, the momentum does not double. It goes all the way down to 0. So that truck stops. So let's talk about the concept of the conservation of momentum. Now, before the collision, the truck has a negative 60,000 newtons to it. Notice that the truck is going to the left, okay? See there? All right. That means negative. It doesn't mean that negative 60,000 is a smaller number than 20,000. No, the negative just means the direction, not the size of the number. The momentum of the car in the beginning is 20,000 newtons. Remember, we took the mass times its velocity to get its initial momentum. So that was before the collision. Now remember, momentum of the system is not going to change. It is conserved, and the system is both vehicles, okay? And when they were moving towards one another, that was their initial velocity. When they collide and move, that is their final velocity. So after the collision, the final velocity of the truck is 0. Well, when you take velocity and multiply it by mass, that is going to be 0. So therefore, the momentum is going to be 0. So after the collision, the momentum of the truck is 0, and the momentum of the car is a negative 40,000 newtons. So once you do the calculation of the momentum of the truck to the momentum of the car, we get a negative 40,000 newtons, which is the same as before the collision, and so conservation was conserved. I mean, momentum was conserved. So, if we look at this problem right now, we have a situation. I'm pausing just a moment. I'm trying to get myself organized here. I'm going to write, this is best practice, I'm going to write the formula. And I'm going to use color coordination to do it. And I'm going to write kind of small, but where you're at, you probably see it just fine. So I've got my initial and my final momentums. My momentums of 1 and 2. And then I've got to get my momentums of my final velocity of objects 1 and 2 on this other side. So notice that I'm writing VF1. Now it's very easy for you to mess this up. So it's not so hard as much as it can be tricky. So I am demonstrating for you the best practice. So it's best that you do it this way to keep it all straight. So now I'm going to read my question, and as I read my question, I'm going to plug in. So I have a 0.5 kilogram object that is traveling 6 meters per second. You can read the English and see how that all works out. It makes a lot of sense. That collides head on with an object that is a 1 kilogram object that is moving in the opposite direction of negative 12 meters per second. Okay? And that is going to be equal to my final velocity of object 1. Object 1's mass has not changed. It's still 0.5 kilograms. But its final velocity is negative 14 meters per second. Plus the mass of my object 2, which still has not changed. That is still 1 kilogram. But the question is asking me to find the velocity of my second object. So that's my VF2. Okay, so that is my unknown. So I'm going to shorthand and call that X as we calculate the rest of this problem. Okay. All right. So if we do this, we're going to take our 0.5 times our 6. And if you didn't already figure that out, that is 3 kilograms times meters per second is Newton second, or Newton, or NS. 1 kilogram times negative 12 is going to be negative 12 NS. Make sure you're writing the correct units. You'll get in trouble if you don't. 0.5 times negative 14 is negative 7 NS plus 1 kilogram X. X is our unknown. That's what we want to find out. That right there. Okay. All right. So let's go ahead and take care of this side of the equation just to get things taken care of. So we're going to take 3 plus negative 12, and that's going to give you negative 9 NS. Okay. So here's my negative 7 NS. My 1 kilogram X. Remember, X is what I want to find out. I'm going to get rid of this from this side of the equation. Okay, so when I bring it over here, what I end up getting is a negative 2 NS. These cancel out. 1 kilogram X. X is still what I want to find out. Now, I've got to get rid of this. And I'm going to show you the work because remember, NS is also kilograms times meters per second. Well, Ms. Klein, why do we have to do that? That's just extra work. Well, no, it's not. It's to ensure that you get the right unit because the kilograms cancel out. Yes, negative 2 over 1 is still negative 2, but we want to make sure that we get the right unit. So the answer is negative 2 meters per second. Okay, so that's how you do this. And so I'm going to toggle it over to example number 2. You do this on your own. Go ahead and pause and see how well you do. When you're done, unpause and you will be able to see me work it out. But I'm not going to be talking. So now we're going to talk about inelastic collisions. A collision in which objects collide and stick together is an inelastic collision. Now, in this situation, there is some mechanical energy that is transformed into heat energy. So these objects will collide and they stick, and they'll either move to the left or they'll move to the right, but they stay together. So the difference in the inelastic collision is that you start out with two separate objects and you end up with one combined object. So our formula for calculating an inelastic collision problem is taking the momentum of object 1, adding it to the momentum of object 2. And those are both your initial velocities there. And that is equivalent to taking the mass of object 1 and 2 and adding those together and multiplying them by their final velocity. So we only have to have one final velocity that is equivalent for both of them because those two objects have stuck together, okay? Now, just like the conservation of momentum was conserved in an elastic collision problem, conservation of momentum is conserved in an elastic collision. Now notice that when the car and the truck collapse this time, or collide this time, they stay stuck together. That was a little bit different from our previous cartoon. Okay, I believe the truck just stood still. But in this particular instance, they all moved to the left. So they had a negative situation here, momentum. Okay, so what I just said is basically what's on this PowerPoint slide. Before the collision, the truck had a Newton of negative 60,000. The car before the collision had a Newton of 20,000. The total system had a momentum, I said Newton, I meant momentum. The total system has a momentum of negative 40. So after the collision, the truck's momentum went from negative 60,000 to a negative 30,000. And the momentum of the car went from a positive 20,000 momentum to a negative 10,000 Newton. So when you do the math, they were both going to the left. So if they're both going to the left, you add them together. You've got your 30 and your 10,000, which makes 40,000 going to the left. So it's a negative 40,000 newtons, and that's exactly the momentum of the total system before the collision and now after the collision. So we have conserved momentum. So let's work a problem. So in our first inelastic collision problem, we're going to go ahead and write down our formula. This is best practice. Now remember, pay attention to what you're doing. So we're adding our momentums of each object just like we did in the beginning of the elastic ones. But on the right side of the equation, we have to take our masses of our two different objects and we add them together because they have become stuck together. And we're going to multiply it by their final velocity. Okay, so there's our formula, and I'm going to plug in. The example reads that a 3,000 kilogram object is moving rightward, which is positive, with a speed of 15 meters per second. And then we had a second object that it collided with, and that object weighed 1,000 kilometers, that's kilograms, excuse me, times the velocity, which is going leftward, which means it's going to be negative. And that is going to be equal to, and I'm just going to add my masses together here because I'm running out of room. Now remember, my VF is my X because that's what I want to find. So if I take 3,000 plus 1,000, that's going to give me 4,000. So I'm just going to go ahead and do that because it's easy to do that right now. 4,000 kilograms. Okay, so now we can go ahead and do the math of our little small pieces here. So 3,000 times 15 is going to give us a 45,000 newtons. And our 10, our 1,000 times 10 is going to give us a negative 10,000 newtons, or NS. All right, so we got our 4,000 kilograms over here. All right, so let's go ahead and take care of our 45,000 minus our negative 10,000, which is going to give us 35,000 NS. And you know what we're going to do here. We're going to divide both sides by 4,000. They cancel out over here. Now remember, this is kg meters per second. So that will cancel out, so I end up with meters per second. Okay. And so your answer is 8.8, and it's positive. It's going to the right. All right, so that's how we do these. So here's example number 4. Go ahead and pause the video, work that out, and then when you've got it worked out, play the video so you can see how it all worked out and see what the answer is. Thank you for joining me on my web tutorial. Have a nice evening.